Hello, Mr. Ryan, are you right? We talk about graph, yeah? What's graph? Can you give me an example? What's a graph?
Tree.
Oh yeah, tree is a graph.
Tree.
Tree, binary tree, yeah?
Binary search tree.
Binary search tree. Graph is a data structure with the vertex and edges. So it's a collection of vertex and edges. Vertex, what's vertex?
Vertex is
Vertex, yeah? Vertex and edges. Okay. Tree is a graph. Graph is not...
vertex are the points of a cube and other other 3D shapes.
Okay. Can you say that again?
Vertex is more than 1 point.
Okay, it's like a node, yeah? A node, okay?
In a 3D shape.
In a 3D shape, yeah. In a 3D space, the vertex, yes. Tree is a graph. Graph is not a tree. It's not essentially a tree, right? Okay. So for example, this vertex, there are 3 vertices, 1, 2, 3, and the edges 1 to 2, 2 to 3. If the edges have directions, we call it directed graph. If it doesn't have any direction, if it can go both ways, we call it undirected graph. Yeah. We have weight on the edges. Yeah, we can say okay, from the cost from 1 to 2 is 2. The cost from 2 to 3 is 4, right? Then we call it weighted graph. Today we're going to introduce a new concept which is called strongly connected component. SCC, okay?
Super cool candies.
Strongly connected graph. Okay?
Strongly connected cats.
So
It doesn't end in a G though.
strongly connected graph. Yeah, it is.
Graph.
Strong connected component. Sorry, component. Yeah, you're right. Strong connected component. Okay.
SC component.
Okay. So look, if what does it mean? It means that if any node, any vertex in the graph is reachable from any vertex. Okay. So if we have this 1 to 2, right? The direction 2 to 3, 3 to 1. Is this a SCC, a strong connected component? Any vertex can be reachable from any vertex. Is it?
Yeah. It's not that strong.
So can we reach 1 from 2?
Yeah.
2, 3, 1. Can we reach 1 from 3? 3, 1. Yes. 2. Can we reach the 2 from 1? 1, 2. Can we reach 2 from 3? 3, 1, 2. 3. Can we reach 3 from 1? 1, 2, 3. Can we reach 3 from 2? 2, 3. Okay. So basically, a strong connected component is that any vertex can be reachable from any vertex.
Does it have that? So does strong connected? What if it doesn't have any arrows?
That's good point. That's a very good point. Okay, so usually, if it doesn't have any arrows, okay, that's a very, very nice point. If it doesn't have any arrows, so it goes both ways, right? If it goes both ways, what happens? If it's a single piece connected component, that's a strongly connected component, am I right? Yeah?
Yeah. Yeah.
Makes sense? So now,
Yeah.
usually we talk about SCCs, we talk about directed graph, okay? So let me give you another example. Is this a strongly connected graph?
No.
Why is that?
2 can't go to 1.
That's right, yeah. 1. We can't go to 1 from any other nodes, right? 2, 3, 4. But these are cycles, they can go from anywhere to anywhere. From here, right? But apart from 1. So you got the concept, SCC, okay? Directed graph, with direction, a directed graph. We want to find out if it's a SCC. How would you usually do it? Forget about the Python coding, whatever. So given the graph, how would you, even you visualize it? We look at it.
We use a dictionary.
How do we check if it's a...
Depth search.
So forget about any algorithm. Just talk to me. Given this graph, how do we find out if it's a SCC? How would you check?
Look at arrows and look for cycles.
Look for cycles and then what?
Arrows. You know that thing?
Errors?
Yeah.
So how? Complete the sentence. How?
We look.
So our task is to find out if any node can be reachable from any node, right?
If you look at it, it has to be like strong and one shape.
In one shape, so it has to be in one shape, connected, yeah?
Yeah, and
Okay,
also...
but connected does not, look, this is connected, but it's not SCC.
No, but I mean, when you look at it, and you look at it, it looks strong and like hardened, but this one tail waggy, which makes it look a lot silly.
Yeah, come on. How about if I reverse the edges? Okay, so now is this a CC?
Let's see. No.
No, why is that?
Because this bit has a waggy thing.
Come on, what? Seriously, what? Why?
Because the arrows and this you can't really go anywhere.
Yeah, 3 can't go. Yeah, exactly. Okay, so look, it's not about the shape. It's also about the edges. Alright?
Yep.
Okay, so how would you do it? I mean, how would you simplify this scenario? Can any node be reachable from any node? Okay, I give you one hint. Okay, come on, I give you one hint. So we want to find out, can any node, any vertex be reachable by any vertex? Yeah, we want to prove this. So how about if I telling you? Okay, so there are 2 things I need to check. The first thing is that if I'm telling you for any single vertex, yeah. For example, if you let's for simplicity, let's just take one. So if I tell you that I can reach any vertex from 1, okay. So basically saying that okay, from 1 I can go from to anywhere else in the graph, okay. Yeah. So what else do I need to prove that in order to with these 2 statements I can conclude this. So I can reach any vertex from 1, and then the second statement needs to be true in order to prove that then any vertex can be reachable by any vertex. So look, I can go to anywhere from 1.
You can reach any V from anywhere.
Yeah, that's the thing we want to prove. But now I can tell you that I can reach any vertex from 1.
It's like I can reach any V from 2. We need to...
Come on, think about it. Look, this is logic. This is not about programming, algorithm, computer science, whatever. It's about the logic. I want to prove that anybody can go to anybody's house. Okay? For example, anybody's house.
So why is it from 1?
I just take any node, for example, right?
Because you live in 1.
Yeah, it doesn't matter. You can take 2 for simplicity, just 1. Okay? Yeah, because look, I want to prove that any node can go to any node, and now I'm telling you that from 1 I can go to any node.
It has
So
arrows.
1 can go to any other nodes, right? For example, this 1 can go to 2, 1 can go to 3, 1 can go to 4, right? So look. From 1 I can go to anywhere. But in order to prove that any node can go to any node, so look, for 2 needs to go to any node. So what does it need to do?
For 1.
Yeah, so 2 goes to 1 and then can go to anywhere, right?
Mm-hmm.
Okay, so what else do I need to prove?
That any V can reach to 1.
Exactly, perfect. That's the thing, yeah? Do you get it? Yeah? Well done, that's very clever, okay? I can go to anywhere. Yeah, I can go to anywhere. I prove that. And I also need to prove anybody can go to me. Right? So then how do we prove anybody can go to anybody? Anybody go to me, and me can go to anybody. So that proves that anybody can go to anybody. Alright?
Mm.
Perfect, yeah? Is it perfect sense? Yeah, so anybody, any V can reach me. Okay? Okay, so the first one is what? Is 1 can go to any V, yeah? Okay, so with these 2, then we can say any V can go to any V, okay? Any vertex go to any vector. You mentioned about the depth search, yeah? We can do this depth search, yeah? Given there are n, so we give a graph. We give a graph with the n vertex from 0 to n minus 1, right? Now we use the depth search. With use depth search, we can prove this from the first point. From 1 to any V with the single depth search. Easy. Why is that? Depth search, recursion. Now we just have to check. We just have to check the visited size if it's equal to n, right? But how do we check any V can go to me with a single depth search? Think of the opposite. What's the opposite? Look.
Any V can go to me.
No. Look, I can go to n 1 to V, 1 to 2. What's the opposite? If I want.
2 to 1.
So I just need to reverse the edge. I reverse the edge and then I do a depth search. Yeah? Then that proves that any V can go to me. Am I right? Make sense?
Mm.
Okay, so let me write this depth search, okay? with the depth search, we can usually write it in two ways. One is recursion. The other one is using the wire, the stack. Yeah. Which one you think is more easy to implement? Which one you think is more easy to implement?
Depth search.
I mean, depth search, there are two ways. The recursion and the iterative. Using the stack, we maintain the stack for ourselves. Or we let the computer maintain the stack by recursion. So which one you think is easier?
Recursion.
Yeah, of course,
Because
recursion.
it's shorter.
It's shorter. Okay. So define check SCC. Okay, check SCC. So strongly connected component. So at the beginning, we given this n, the number of vertex, and we got given these edges. First of all, we need to define a check function. Okay, check function. We start with the current node. Yeah, we want to do a depth search. We want to do a depth search from current node to with this graph, right? Using this graph, we have a this scene equals hash set. Okay, set is a hash table. Okay. So this scene is used to remember the number of vertex we have visited. So we do a depth search from the node 0 or node current, and then we just have to check if the size of the visited scene is equal to n. And if it's n, that means that I can visit any node from current. Okay. Define depth search. We can define a function inside a function. Look, this is define. We have a list define, and we have another define. Okay, we have a define function from another inside another function. We can have a listed define function. Okay. Depth search current. So look, if we have seen this vertex before, then we just return. And otherwise, the first thing to do is to add it to the notebook. Yeah, scene.add current, and then for I in graph, we use the adjacent list. So basically, G1 equals 2, 3, 4. What does it mean? It means that the vertex 1 has the edges to 2, 3, 4. Okay, that's what it means. The G is the default dictionary, and the default dictionary, the default type is the list of integer, list of vertex. Okay, and then we just have to do depth search I, right? And then look, we do this depth search with the current, and then with the current, and then we just have to check return length of the scene if it's equals to n. Depth search. Okay, so this function we want to check if from current can we reach any node in the graph. That's what it means. The scene is a hash set, the notebook. It stores the vertex we have visited. And then inside we have another depth search. Look, depth search. We have defined another function with the current. Look, if the node is visited, then we just return. Yeah? And then if it's not visited, the first thing we remember we have visited. And then we go through it's connected. It's a connected vertex, and we do the depth search. This is recursion. Yeah? Here, this is the recursion, okay? This part, yeah, recursion. And then we do this depth search, and we just need to check the size of the visited node is n. Okay? And now look, the first thing to do, we do the graph. G equals default dictionary. At the beginning, we have a graph, adjacent list. And then for A, B in edges. Then G, A dot append B. And the reverse graph, why do we need to reverse the edges? We want to check if any node can reach me, right? So the simplest way we can do is reverse the edges. Yeah, look, we want to check if anybody can reach me. Now we can reverse the edges, right? If we reverse edges, look at, for example, 2 to 1, 3 to 1. Now if we reverse edges, then becomes 1 to 2, 1 to 3, then we can start with the node. Right? We start with the node, and the problem becomes the same as checking if the node, if we can visit any node from node 1. Okay. G slash equals the same default dictionary list, and for A B in edges, this is the same. Yeah. For A in edges, G reverse edges. How do we reverse edges? Look, A B A. There's an edge from A to B. How do we reverse the edges? Look, GA append B. So how do we reverse the edges? You can get this one.
GB open A.
Perfect. Yes. GB the open A. Okay. And now we have this G stash. Then we just have to do this check. So return check. The last thing. Return check. Check. Let's start with the 0. Yeah. 0 G and check 0 G slash. Okay. How do you call this?
Apostrophe.
Apostrophe. Okay. Okay. So this is the reverse graph. Okay. We reverse the edges, and then concludes the prove that any node can reach any node. Okay. The time and space complexity for the single depth search, the time and space complexity is O V plus E. Okay. V number of vertex, E number of edges, and we'll do this twice. So it's G. This times 2, and when we talk about complexity, we drop the constant so that the time and space complexity is still OV plus E. Okay. What's the SCC, and how do we check if a graph is an ACC, and what's the approach? And what have you learned today? What's new? Have you learned something new today? Come on,
Yeah.
that's it. Yeah.
If,
Okay.
If we can, any V can go to any V.
Okay. So what's V? What's SCC? Strong connected component in the graph.
Yeah.
So it means that if any vertex can be reachable from any vertex, right?
Yeah.
Okay, so we're given a directed graph, directed unweighted graph. Okay, it doesn't matter if it's weighted or not. Directed weighted graph. Usually, if it's undirected, it means that edges go both ways. Then it will be very easy to check if it's a STC, right? We just have to check if it's a single component, right? Am I right? Yeah. But for the direction of directed graph, how do we prove that any node can be reachable by any node? So how do we check? We need.
Like one can go to any V and any V can go to one.
Yeah, then that concludes this. Any V can go to any V. Yeah. Yes. Okay, so that's it for today. Bye bye.
Bye.
Bye bye.